Hi. That's not a processor. That's a processor. This bad boy is 600 watts power dissipation, 2,772 pins. Is that a socket? 2772? I guess it is. It's got 121 dies installed. It's 63 layers. It's liquid cooled. It's automatic. It's systematic. It's hydromatic.
Ultramatic. Why could be greased lightning?
Thank you very much, Jim Ranieri, for sending this into the mailbag. I had to do a separate video for this. It's so cool. This is an IBM 9121 processor module, which comes out of a System 390/ES9000, whatever you want to call it, parallel enterprise server from 1991. This thing is a beast, and we're going to tear it down. So let's just toss this little pathetic thing away. Check it out. There's the date code there. No, a second week, 1991. I can't make heads or the tails of the part numbers on this, but I do believe it is an IBM 9129 processor out of a processor frame for a System 390 ES9000 server. It went under different names. It's kind of weird. If anyone knows the exact story behind that, some people they actually branded it System 390. Other times they branded it ES9000 or something apparently. And anyway, this is a state-of-the-art mainframe processor from the early 90s. Oh, and it's just, look at it. Oh, thing of beauty. This is joy forever.
Behold the Wonkamobile. Thing of beauty is a joy forever.
We've got a gigantic ceramic substrate in here. As I said, 2,772 pins on this bad boy in a gigantic metal frame that weighs 2.2 kilos. Just the processor module in each frame, like a physical frame. I'll try and find a photo. It actually had two of these processor modules, I believe. Back then, it was a big deal. No, I didn't just crush the pins because it has little tabs on the bottom. It's got individually engraved numbers on it. So I don't know, they tested and would have tested and maybe characterized each individual one back then. And I found an old ad in a magazine back in the day that the IBM 9121 processor system went for up to $1.5 million. I don't think that was just this module. It was probably only a couple of $100,000 for this module, so cheap as chips. This is $1991 too. None of this modern 2020 fiat currency rubbish. Now this has around 20 MIPS or 20 million instructions per second, and as far as processors in the early 90s go, we're talking an 80486 processor back then. I believe that came out in 89, but basically that was still the top of the range processor. The highest speed version, I believe the 50 megahertz of the 80486, ran at about double that. It was about 40 million instructions per second. So this thing wasn't exactly state of the art in terms of MIPS processing power compared to desktop PCs of the day, but you've got to remember this is a massive mainframe processor system designed for huge amounts of data processing and other stuff, and this could access up to 9 gig of memory per processor. That doesn't sound like a lot these days, right? 9 gig of memory, but back in 1991, whoa, this is heavy. And of course, heavy it is. As I said, this weighs 2.2 kilos just for the processor module itself. And this package is actually called a TCM, or a thermal conduction module, because it actually came in two types. Obviously, these pins, the 2,772 pins on it, they connected down to a matching socket in this thing. But these processors actually had a huge heatsink on top of them that weighed 5 kilos or something like that. And I believe these came in both air-cooled and water-cooled versions. And here's a picture of what one of those would have looked like. So there were, as I said, two of these modules per physical frame, they called it, which held the two processors and had all the wiring and other support stuff and the power supplies and the cooling infrastructure and things like that. So yeah, this thing could dissipate up to 600 watts. There's 121 chips, or up to 121 chips, and they can dissipate up to 10 watts each for a maximum module power dissipation of 600 watts. So, yeah, this little pissant thing. So let's take this puppy apart first. We get this frame off, And check this out, just notice this little tab on here. I reckon that is for a thermocouple to measure the temperature of this thing. Yeah, most likely, I'd be stunned if they weren't measuring the temperature of this thing. Look at all these screws to hold it down. I believe it is oil filled inside, like the entire substrate filled with oil, and we'll see a whole bunch of heat sinks as well. Oh, yep, can crack it. This could take a while. Yes, I do have an electric screwdriver, but not one that supports this tip. I just unscrewed the last screw. Damn, I didn't have the camera running, and I heard this and like big O-ring seal in there. I don't know. Oh, can you? Oh, I'm not sure if you can hear it. Hang on. Now I'm just deciding which is the best orientation to lift this up from. Oh, I can see in the back. I'm having a peek. And I know that this will be the most impressive if I lift it up like this. Actually, I have to cut along there. So, sorry for all you purists out there. But we're going to avoid the warranty on this bad boy. Oh, and a million voices just cry out in... cry out in anger. All right, here we go. Are we ready? Rolling camera, because I only get one take at this, I think. Whoa! Look at that. Whoa! That is gorgeous. That is processor porn right there. Wow. Wow, wow, wow. Look at the individual copper heatsink slugs on each little chip inside there. And yes, there is a thin little layer of oil, but it hasn't oozed out or anything. You can see the O-ring seal around the edge there. Wow. It's just brilliant. Yes, they all have shifted. They all should be nice, evenly spaced, but absolutely beautiful. And you can see that they all go into individual little machined slots in here, which, by the way, have little springs in them. Check that out. There's actually little springs inside each one of those. Not all of them are populated. There's some that actually don't have any heatsink slugs at all. But yeah, there's little springs down in there to keep the pressure, keep the tension down on the die. And you'll notice there that some of them just don't have dies installed in them. I don't know if that was like just an optional thing, but it looks like the pattern is there. I'll show you a closer up later, but yeah, it looks like the die pattern is there, but anyway, these are like flip chips. These are chip scale packages. So they're, it's like from 1991. Whoa. So you can see why this is called a TCM or thermal conduction module, because it's all about the thermals. It's all about getting the heat out of each individual die on there, each individual chip. And as I said, each chip can dissipate up to 10 watts. So one of these solid copper slugs here, even though they don't actually have direct contact to this, except on the sides, I guess their fit is, if I can take, oh yeah, their fit is very, oh yeah, hang on. Here we go. Here's one of these copper slugs, and they just fit brilliantly, and I can see the oil, the bubble oozing out, and look at that. Oh, I could play with that all day. Oh, that's just beautiful. Absolutely beautiful. So yeah, they don't have, well, the mineral oil is going to be heat conductive as well. So, you know, it's going to have an extra bit of thermal resistance in there, but anyway, that's how each one of those individual dies can dissipate up to 10 watts with a maximum module dissipation of 600 watts. It's just, oh, it's fantastic. There's some of the pattern on an unpopulated chip. Look at that. Wow, that's really something. And I know you want to know how many vias and what via hole sizes we've got on here. We're talking 78,500 of them, and they're 100 microns a pop. Now I'm actually going to get all of these heatsink slugs off here, and I'm going to put them back over here, so this could take a while. And they do have like a little knobby bit on the top, little nib on the top, and that goes down into the spring just to center the spring on this thing. So anyway, I'm going to stick them in, and you know which ones actually, which holes are populated because they've got springs in them. The ones that don't have springs, I won't put a copper slug in there because it might be hard to get out. Geez, there's a lot of suction on there. You've really got to get them off at an angle. And, well, those springs, yep, the springs will self-realign, so that's nice. Obviously, the manufacturing process is not as messy as the disassembling process. This is ridiculous. What am I doing? So I'm not sure what sort of mineral oil this is, or what sort of oil. Seems some sort of mineral type oil. In the seismic industry, we used to use Isopar, or Isopar M, I think it was. So you can go look that one up, and we had a license to use that with these gigantic tanks of it, just filled with, because it used to, we had one tank that was just filled with Isopar, but that tank wasn't just a tank, it was like part of the manufacturing, these slippery little suckers, part of the manufacturing process where we would put the outer skin onto a seismic streamer, and so the outer poly put the kettle on skin was got to get the right way up. It was like extruded, kind of, for want of a better term. Oh, there's a little something or other there. It was like extruded out of this machine that was this big drum that was filled. I'm talking bigger than a human sized drum, like 7 foot, 8 foot tall or something. And it was, there would be extruded out of that, and it was just filled with Isopar, and we'd have Isopar all over the floor, and it was just, yeah, fun stuff. Okay, that one doesn't have a spring, so I'm going to give that one a miss. It's only like 4 or 5 that don't have springs. Oh yeah, I've broken off. Are they like little bypass caps in there on the ceramics? How would they like just come off like that? There's a couple of them. We'll have a look at those under the microscope. But surely, like, I'm not putting much force on these at all, so I'm not sure why they wouldn't just fall off like that. Unless there's some sort of, like, they're not actually soldered down. There's another one. There's another one right there. Look at that. Cannot explain how unusually therapeutic this is. Yeah, I think I'm just breaking off all those little brown, what look like caps, but I don't know unless I get them under the microscope. And, no, that's all correct. I got them all in the correct order. 1, 2, 3, 4, 5, 6 unpopulated chippies, and they didn't put the springs in. And, these are, I don't want to, but, this is just so much fun. Oh, boy. I wish this was field of vision. Wow. Anyway, yeah, we've had some of these little chippy things come off, like half a dozen of them. So I'm not sure what the deal is. But I'm going to, I'll just leave this gunked up, and I'll just get some paper towels and wipe off all this, because it'll be easier to see under the microscope and the macro lens for the chip. So I'll get back to you. Ugh. Anyway, that is the module in glorious 4K still with the mineral oil on it. And you'll notice that they're not all identical. Why aren't they all identical? Because these modules are supposed to contain SRAM chips as well. 128K bit SRAM chips. And I'm guessing that these are down here. Why they're kind of like oddball, sort of not really, symmetrically placed, I don't know. But anyway, like, I assume that they're different types, but even they're a different color, slightly different color to those ones. And look, that could just be light refraction. of the dies because, well, that's what dies do. Pesky little things to look at. And, well, quite beautiful, actually. You get them under the right light and they're quite spectacular. But, yeah, anyway, this is not just one module with like 121 different processors on it. It's got tons of different logic elements, including 128 kbit SRAMs, and that was pretty huge for 91. And they're 10 nanosecond access time SRAMs too. Actually, it seems to be near impossible to just wipe this oil off. Yeah, there's another one that, yeah, I can see the pads on the bottom of that chip, so they're coming off. So these are not soldered down. I reckon these are just, well, are they just press fit? Wow, that'd be interesting. I don't even know if soaking the whole thing in isopropyl will do the job, because, yeah, that oil's going to be hard to get rid of. Well, that's how you drop the frame out. I just put it up here so to raise it up, just so that I can take some macro photo shots. Always, my teardowns usually always have high-res teardown photos over on my Flickr account, so check that out. And the whole thing just fell off, so we're left with the ceramic substrate, which is pretty groovy though, so anyway. I'm really having some fun taking photos of all this at like different angles and stuff. It really is just quite something. And I can of course adjust the iris. f3.4, that's the lowest my camera will go at this zoom. If I increase our aperture, everything becomes in focus, or mostly. And let's check this out under the Tegano. Now this is manufacturing material science at its absolute finest. It's like absolutely phenomenal. I'll link in the paper down below. You can read it for yourself, talking about all of the construction technology that goes into this. But we're talking about a 63-layer ceramic substrate here. As I said, 121 devices on here, 144 caps all in here. We'll take a look at those. Each chip has 648 pads on it. We'll check that out closer up. A mix of CMOS and bipolar technology devices, by the way. And there's 78,500 vias on this thing. I mean, it's just absolutely incredible. And each chip there has 648 pads. And this is not a PCB, okay? This is a ceramic substrate with a mixture of thin film and thick film hybrid layer technology. So I believe the top layer is thin film printed and the inner layers are thick film printed. Now those 63 layers, 0.2 millimeters, that's 7.8 thou thickness each. We're talking about 12 micron conductors. That's like half a thou. Half a thou conductors on this thing. So yeah, it's just absolutely nuts. And the top ceramic surface layer has a surface flatness of 5 microns. So all the mechanical engineers out there probably getting moist over that. I don't know. Let me know. Is that good or not? 5 micron flatness over this entire module. So the ceramic substrate here is made with a mixture of alumina powder, glass powder, organic binder and plasticizers and all sorts of stuff. So, you know, really just incredible material science involved in this. The manufacture of this board. Anyway, you can see the capacitors down here, and let's find one that's ripped off, because I did rip off a few. There we go. There's the little pad for the capacitor down there, and yep, I can feel that. Oh, look at that. Look at that. The solder, I'm going to use that term in quote marks, the solder, look at how I can just, like, this has not been heated up at all. So they're obviously using some sort of, weird-ass metallurgy here for the solder on these things. I'm going to assume that it's the same for the chips as well. But there for the capacitor, there's the capacitors, okay? I'm going to try and get this off, okay? I'm going to put a little bit of force on that. Tongue at the right angle. Yeah. She's budging. There it is. There it is. Have you ever taken off a chip with that sort of ease? Oh, this is magical. This is, and floating around in oil. Oh, this is my favorite thing ever. This is just incredible. A floating oil, a capacitor floating with oil. Oh my goodness. Which you can just imagine being able to take off chips with that sort of ease. Oh, Lewis Rossman, eat your heart out. Okay, people are going to be horrified, but I'm going to try and do this with one of the chips. Oh, people are going to be more... I mean, we've got like hundreds more pads on here. Hundreds and hundreds of more pads. But let's see. Oh, no, I'm putting a lot of force on that. Oh, I'm putting all... Oh, my hand's slipping. Don't you hate it when your hand slips due to the oil? Jeez. Yeah, I can't make that budge. But certainly, the capacitors, piece of cake. They just go off like that. Oh, this is so much fun. Oh, this is great. Let's flip there's our cap. There you go. We flipped our cap over, and there it is. 16 pad capacitor, which looks like it contains, because we saw the top of it over here, does it contain 4 individual caps like that perhaps? I don't know. Anyway, you can see that they're just like, there's no traces coming off there. They're just buggering off down in the internal layers, and you can't see through these layers because they're like ceramic. They're a ceramic slurry substrate. And as I said, like individual vias down in there, we're talking 100 micron holes. And these are all, you know, like, I don't know, test pads. Not sure what the deal is. I assume, you know, some sort of test pads, something like that. I'm never going to get this oil off. I'm not even going to try. I'm already starting to get oil over everything here. So, yeah. But anyway, this is absolutely remarkable. We've got 648 pin. So I guess you could call that BGA. Although, you know, they wouldn't have used that term back in the day, I don't think. And the inner layers apparently are made of a molybdenum, if I'm pronouncing that correctly, molybdenum powder. So yeah, these are not like copper exposed etched PCBs. This is not what's happening here. This is an entirely different technology to what you're used to with your fiberglass circuit boards. It's just, yeah, it's not the same thing. All right, I'm going to get medieval on its ass. I'm going to get in there with a big pair of pliers. Oh, sorry, this is going to flame comment down below. Go ahead. I don't care. I'm going to give that a little twisty. Life's pretty straight without twisties. Oh, yeah. No. Oh no! I've come a gutser. Look at that. But at least we can see under it. We can see under it, so that's useful. There you go. Wow. Okay. Yeah, you can see a similar thing to the caps in there. You can see the individual solder pads. Once again, look, I'm going to clear this away. Yeah, look. Look, you can see the solder. Yep, it's the same thing. It just spreads like that. So this is not your regular solder that you are used to. Because this is room temperature here. This has not been heated up. Wow. So yeah, we just completely shattered that die. Just absolutely butchered it. Sorry about that, but that's fascinating to see under that and confirm that it's basically the same interconnection technology as what was under the capacitor there, which makes sense, of course. So is this some Doug Henning metallurgical magic? Well, I don't think so. I had a look at the document and it actually specifies, yes, it's solder, and it specifies it as 97.3 solder. So not that 60-40 rubbish, but yeah, 97.3. It's not some magic room temperature solder or something like that. So I've got to assume that's what's here. So why does it seem to wipe off like that? Well, I can actually, this is not feeler vision, but I can actually feel the bumps in there. what's actually happening here and why I was able to magically use the Jones method for desoldering this chip, just push it right off, is because of the tiny pitch and the tiny amount of solder that we've got here. We're talking 16 pads here, but these pad dimensions, I checked, are only 180 microns wide. So that's like 7 thou wide pads on here. So there's practically no solder on there. These aren't balls on the bottom of the chip, right? These are just like, they've just applied the solder paste however they apply it, and they've reflowed it, you know, in a not too dissimilar manner to what you're used to. But there's just such a tiny little pissant amount of solder on there that the sheer force of that, just my force was enough to just break all of those pads at once. It's only 16. I guess the mechanical engineers out there, please, you can, you know, if you can do some sort of shear analysis or something. I'm probably not using the right terminology, but anyway, with 180 micron wide, 97.3 solder, you'll probably find that, yeah, you can just push these chips off with a bit of force. Now, why don't the pads rip off? Because this was what would happen if you tried this at home. Don't try it at home, kiddies. The pads will just rip right off a regular fiberglass board, even the real high quality, high temperature ones, most likely, because, you know, a tiny little 7 thou pad in there, 180 micron pad size, there's going to be virtually no adhesive under there, although it might not come off because you got the veer in the middle, but I don't. Anyway, if you relied on a tiny little pad like that, there'd be virtually no adhesive on there to hold those pads in place, and you'd just shear them all off. You'd completely kamikatze, and yeah, do not try the Jones method for desoldering your BGA parts, because it's not going to work. And look over here, we haven't ripped off a single pad. Why is that? Is because, well, this is like, you know, this is what you get when you pay, you know, like $100,000. This is like, you know, the best that the IBM research scientists can come up with. This is, you know, not just regular fiberglass. This is like, you know, some ceramic woo-woo mixture of stuff, and it's all just embedded in there. And these pads are, they're probably never coming off. I put a lot of force on that. Anyway, that'd be fantastic if you could repair chips like that. But unfortunately, yeah, don't try it on anything but IBM magic woo-woo. So I mentioned this document, and I won't go through it. I'll just link it in down below. But it's done by J.U. Knickerbocker. Winning name, and friends, of course. And it's basically them. They're a bunch of, you know, IBM research scientists. It's basically them boasting about all this marvelous technology that they've got in these, you know, ceramic modules, in the construction of them and everything. And it's highly recommended, worth a read, absolutely fantastic. So just think of the people that went into actually making this thing, and the technologies involved in manufacturing this, and they're thanking these various divisions within IBM for doing it. Anyway, J.U. Knickerbocker apparently had a distinguished career at IBM. I don't know where he is now. He published like 90 papers or something. I had a look. Impressive. So there you go. I hope you enjoyed that as much as I did, and I've got oil all over my fingers. And thank you very much, Jim, for sending this in. This was absolutely pornographic technology, absolutely fantastic. I'd love to, like, maybe, you know, like X-ray this or something like that. I don't know what we'd see. You just see 63 layers of interconnections and stuff like that under here. So it's got 400 meters of wiring inside this, by the way, for those wondering, which doesn't sound like a lot, but I guess it is when you stretch it all out. Anyway, yeah, 63 layers of state-of-the-art ceramic PCB manufacturing technology from 1991. Absolutely incredible. And this had like half the number of MIPS as an 80486 at the time. But as I said, you know, you're not comparing apples to apples there. So, wow, that's absolutely incredible. Hope you enjoyed that as much as I did. If you did, please give it a big thumbs up. And as always, you can discuss down below or over on the EEVblog forum or over on all of the alternative platforms that I'm on. And I'm also on the Twitters, I'm on the Instagrams, I'm on the Flickrs, I'm everywhere. Catch you next time.